Good evening, students.
Good evening, sir.
Good evening, sir.
Good evening, beta.
Good evening,
So
sir.
basically, this is a class for nuclear physics. In this class, we will discuss different aspects of the nuclear physics. So first, I will introduce this subject with the syllabus we will discuss throughout this lecture classes. So first, I will discuss the syllabus that I am going to discuss. So syllabus for nuclear physics. Syllabus. So first, we are going to talk about the general properties of the nuclei. So first, I am going to talk about general properties of nuclei. General properties of nuclei. Actually, nuclei has different type of properties, like it has particle properties. It also has the wave properties, as well as few of its properties are related to the quantum properties. So we will discuss all these properties one by one. We will start with nuclear radius. We will start with nuclear radius. We will discuss how this nuclear radius is calculated in the historical point of view, as well as which formulas and different type of methods which we are going to which we will use to calculate the nuclear radius, like mirror nuclei method is there, and there are some other methods. So we will discuss.
सर वीडियो ब्लर हो रहा है, क्लियर साफ नहीं चमक रहा है.
Okay. So basically, we are going to discuss all these methods with the help of which we can calculate these nuclear radius.
Okay, sir.
After this, we are going to discuss the nuclear mass. Nuclear mass.
Sir, it's again getting blurred.
Sir, ये
नहीं, now it is correct, na?
Sir, it's on defocus. It's on automatically focusing.
Okay,
mode.
it will take 1 or 2 minutes. Okay, don't worry. So first we will start with nuclear radius, mass, nuclear mass, its density. We will discuss density. Then we will discuss angular momentum. Angular momentum. Magnetic moment. Magnetic moment. Isospin.
सर ये बोर्ड ठीक नहीं दिख रहा.
ठीक नहीं दिख रहा?
सर सब कुछ ब्लर हो रहा है.
Sir, video is blur. Automatically, it's getting blurred.
Okay.
सर कैमरा मैनुअल पे करके फोकस हो जाएगा.
1 minute, please. Isospin. After this, we will discuss quadrupole moment. Quadrupole moment. We will discuss statistics, different statistics associated with the different nuclei. Parity, we are going to discuss, and then binding energy. And last is
सर बोर्ड में
अरे पता नहीं क्या हो रहा है.
सर आउट ऑफ फोकस ऑन होएगा, आउट ऑफ फोकस ऑफ कर दो.
बेटा आउट ऑफ फोकस तो मैंने किया हुआ है, वो पता नहीं कैसे हो जा रहा है अपने आप.
सर उसे मैनुअल पे कर दीजिए तब ठीक हो जाएगा।
हाँ
एक्चुअली टच स्क्रीन से हो जाता है अपने आप, इसमें टच स्क्रीन वाला वो है, लेकिन अपने आप रिमूव हो जा रहा है, कभी होती नहीं है प्रॉब्लम। वी हैव टेकन लॉट ऑफ क्लासेस। बेटा ऑटो फोकस का इसमें ऑप्शन नहीं आ रहा है ऑफ करने का, स्क्रीन टच करने से हो जाता है। तो दिस इज द फर्स्ट टॉपिक वी आर गोइंग टू डिस्कस। सेकंड, आफ्टर दिस वी विल डिस्कस different nuclear models. Second topic is nuclear models. Nuclear models. In nuclear models, I am going to discuss liquid drop model, liquid drop model, then shell model, and after this, I will discuss collective model. Collective model. So we are going to discuss these three models in detail. And you always find out that questions in journal, they are related, whatever question is coming in the exam related to nuclear model, they can be solved with the help of these three models. So I am going to discuss all these three models in detail. After this, we will discuss nuclear forces. Third topic is nuclear forces. Nuclear forces. In nuclear forces, first we will discuss neutron nuclei. We will discuss neutron nuclei. Actually, this is a bound state of two nucleons. This neutron nuclei is the bound state of two nucleons, one proton and one neutron. So basically, with the help of this nuclei, we can understand the various aspects of the nuclear forces. Here we will discuss spin state. Here we will discuss spin state. Number two, we will discuss magnetic moment. Magnetic moment. And third will be quadrupole moment. So with the help of this two nucleon bound state, we will draw few conclusions and then we will summarize these conclusions, and after this we will discuss meson theory of nuclear forces. So in last we will end up this topic with meson theory. Meson theory. So this is the first part of your nuclear physics syllabus. This is the first part of nuclear physics. So in first part, we will discuss in journal. First, we will introduce journal properties. What is the meaning of these terms? What are the expression for these? And then whatever result we will get from these terms, we will try to explain these properties on the basis of nuclear model. So first, with the help of experiments, people have find out different properties of the nuclei, and later they explain these nuclear properties with the help of some mathematical models which are developed one after the another. So on the basis of these three models, I will try to explain, or we will try to find out or justify all the formulas we are going to use here. So these three models are very important. So you should remember one thing in case of nuclei, that all the nuclear properties cannot be explained with the help of one model. Like for binding energy, we will use this liquid drop model. For the spin and parity, we can use shell model. And for different type of excited states which are associated with different nuclei, they can be explained on the collective model. So these models are able to explain few properties, but in general, most of the properties can be explained by these three models. Next, all these properties, in all these properties, a special type of force is playing its important role, that is nuclear forces. Now we will try to understand how this force generates and what will be its consequences on different properties. So we will start with neutron nuclei, 1s2 nuclei. So here in the nuclei we have one proton and one neutron. So this is the best method to understand the interaction between two nucleons. We will draw various conclusions by studying this neutron nuclei, and later on we will summarize all those things with the help of meson theory. So this is the first part of your nuclear physics syllabus. Now come to the second one, fourth topic. So this is first part. Now fourth topic is radioactivity. Now fourth topic is radioactivity. Radioactivity. So in radioactivity, first I will start important terms like what is decay constant, what is half-life, what is mean lifetime. I will discuss all these things, but the most important thing I am going to focus is the rate equations. Here, most important thing is rate equations. How can we write rate equations for different nuclear processes, nuclear reactions? Rate equation. This is the first topic of radioactivity, which I am going to discuss with you. And now on the basis of this rate equation, I will discuss the equilibrium that can exist in radioactive series. Two types of equilibrium I will discuss. So next topic will be equilibrium. Equilibrium. And here in equilibrium, I will discuss two topics or two types of equilibrium. One is known as secular equilibrium. Secular equilibrium, and second is known as transient equilibrium. Second is known as transient equilibrium. So first, we will consider radioactive as a process, and with this process I will define what is the meaning of half-life time, mean lifetime, decay constant. We will be able to find out their number after time t. It can be one-step process like A type of nuclei is decaying into, so it can be one-step process. A type of nuclei is decaying into B. So we will calculate the number of B type of nuclei after time t. It can also be two-step process. Suppose A is decaying into B and B is decaying into C. So what will be the number of B after time t, and after time t, what will be the number of B and C and A? So we will discuss all these things. But here, this radioactivity is due to three types of emissions. It is due to three types of emissions. One is alpha decay, another is beta decay, and then gamma emission. So three types of emission is there. First is alpha decay. Alpha decay. In alpha decay, first I will discuss all basic things, whatever is observed about their spectra. Later on, I will discuss how this decay is taking place. So I will discuss Gamow theory. Gamow theory. Then we will discuss alpha spectra. Alpha spectra I am going to discuss. And different selection rules which are associated with this type of emission. And different selection rules associated with alpha particles. There are two types of selection rules. One is associated with angular momentum quantum number, and second is associated with respect to parity. So parity should be conserved, angular momentum should be conserved. So these two conservation is represented in terms of selection rules. So I'm going to discuss all the selection rules here. After this, I will discuss beta decay. Beta decay. Here we will discuss mainly on quantum theory that is given by Fermi. Automatically, first we will discuss Pauli's hypothesis, and then we will discuss Fermi's quantum theory. Fermi's quantum theory and Pauli's hypothesis. So we are going to discuss this thing. After this, certain beta decays are possible. In another case, beta decays are not possible. So this is all done on the basis of selection rules. So I will also discuss selection rules here. So this is related to beta decay. Third decay is gamma decay. We will discuss what is the cause of gamma decay, what are the selection rules, and what are E1, M1, E2, M2 like of emissions. So basically, there are two causes for gamma decay. Origin of one is magnetic, and the cause of another type of emission is electric. So there are two types of gamma emission. One is due to the electric origin, another is due to the magnetic origin. So basically, we will be able to define, okay, this emission is due to the electric dipole, this is due to the electric dipole, this is due to the magnetic dipole, this is due to the electric quadrupole, this is due to the magnetic quadrupole. So we will discuss all these things here in gamma decay. And after this, fifth topic is, this is the second part. First topic of second part is radioactivity. In radioactivity, I am going to discuss alpha, beta, gamma decay. Electron capture I will discuss here. Auger effect is also, I will also discuss here. So these are smaller topics. I'm not going to mention this. And second topic of part B is nuclear reactions. Nuclear reactions. Nuclear reactions. So we will discuss all three types of nuclear reactions: exothermic, endothermic, and elastic. So I am going to discuss all three processes on the basis of Q value. So on the basis of Q value, we will discuss exothermic, endothermic, and elastic collisions. So I am going to discuss all these three. After this, there are two specific types of nuclear reaction. One is known as nuclear fission, and second is nuclear fusion. We will try to search or find out the causes of this and consequences of this. What are the causes of nuclear fission and fusion, and what are the consequences? In which type of nuclei this type of fission and fusions are most probable to take place? How much energy will be released? Why this much amount of energy is released? I am going to discuss all these things in this nuclear reaction topic. So this is the fifth one. This is the second part. This is the second part of nuclear physics. And the third part is a separate one, that is elementary particle. Elementary particles. So this is a bigger topic, elementary particles, and here in this topic you have to remember a lot of things. You have to mug up many things here. So we will discuss all four types of elementary particles like mesons, leptons, hydrons, everything, and all type of interactions like strong interaction, weak interaction, gravitational interaction, and electromagnetic interaction. After this, we will discuss quark model, and everything, whatever is there in elementary particle. This is a bigger topic, and in this topic, most of the thing you have to remember. You have to remember many numbers which are known as quantum numbers. So in general, what we do here, we discuss these 5 topics first, and we will discuss this 6th topic, elementary particle, later on when your exam will be nearer. And the reason for this is very simple, that this topic is very important. This topic is very simple, but here you have to remember many things. So it will be very helpful if we discuss this topic when your exam will be close. So otherwise I will discuss all 5 topics here, and this we will discuss this separately later on, this elementary particle. And reason for this is it will be very helpful for you. We have seen many times, then when we discuss this topic very near to the exam, you even don't need to remember many things, because we will discuss all those things in the class, and if you are very attentive in class, there is no need to remember those things. Even you will mug up in the class only itself. So these 6 topics I am going to cover here in nuclear physics course. So this is the syllabus for this course. Now, ठीक है बेटा? तो मेरे हिसाब से इसके अलावा कुछ है भी नहीं बेटा आपके सिलेबस में न्यूक्लियर फिजिक्स में, which we have to discuss. Now I am going to start the nuclear physics. So if you consider an atom, we are starting from very basic. So if you are considering an atom, then in the atom at the center you will find a massive nuclei. Most of the mass of the nuclei is concentrated in the central part. The size of the central part is very small. It is roughly of the order of 10⁻⁻15. And size of the, if you find out the radius of the atom, it is in angstrom. So out of angstrom radius, only 10⁻15 meter radius is the region in which whole of the mass is concentrated. And inside this nuclei, you have 2 types of particles. One is proton, another is neutron. As the name suggests, proton carries positive charge, and neutrons are neutral particles. They don't carry any charge. So these protons and neutrons, their masses are nearly equal. They are heavy particles. Their masses are nearly equal. However, mass of neutron is little bit higher as compared to the proton, but you can consider that this is nearly constant, roughly 1.66 into 10⁻27 kg. So these are protons and neutrons. And outside the nuclei, we have electrons, which are revolving in different orbits. And by chance, the total charge on the electron is exactly equal to the total charge on the proton. Due to this reason, the atom in general is neutral. Atom in general is neutral because total positive charge is equal to total negative charge. Negative charge is due to the electrons. Positive charge is carried by the nuclei, and these protons are carrying this positive charge, and they all lie inside the nucleus. If we consider the mass of the electron, which is negligible as compared to the mass of the proton and neutron. Mass of the electron is 9.1 into 10⁻31 kg. So here we have 10⁻31 as a power, while in proton and neutron it is 10⁻27 kg. So there is a large difference between their masses. So you can assume that mass of electron is negligible as compared to the mass of proton and neutron. Due to this reason, most of the mass is concentrated in protons and neutrons, which lie inside the nuclei. So this nuclei is responsible for most of the masses. If you consider electrons which are revolving in the orbits around the nucleus, they are responsible for the chemical properties. They are these valence, you can say in general, the valence electrons, they are responsible for the chemical properties, and you will find out that these protons and neutrons, they don't have any significant effect on the chemical properties. They don't have any, they are not playing any role in the chemical properties. All these in an atom, inside the nuclei, we have proton plus neutron. Outside this nuclei, we have electron. So how can we represent a nuclei? How can we are going to represent a nuclei? We are going to represent a nuclei. Suppose that nuclei is X. So here this will be Z number, this will be charge number or atomic number, and here this will be ZXA. This is the mass number. So any nuclei is represented as ZXA, where this Z is the charge number, this Z is the charge number or atomic number, and this Z number is always equal to number of protons. Number of protons.
Out of
So basically this ZXA here, this Z is equal to number of protons. You have to remember that this number Z is not equal to number of electrons. This Z number is always equal to number of protons. The reason for this is electron can be removed from an atom, but they can be added to some atoms, so ions can be formed, positive ion or negative ion, so number of electrons can change, but number of protons inside the nuclei, they cannot change. If you remove one proton from the nuclei, then this atom will change. So whenever you are writing this Z number, that is always equal to number of protons. And this A, this is known as mass number. This A is known as mass number. This is equal to number of protons plus number of neutrons.
सर ये बोर्ड प्रॉब्लम
कोई बात नहीं बेटा, हो जाएगी सही, थोड़ा पेशेंस रखो, हो जाएगी सही. So this A number is equal to number of protons plus number of neutrons. So in this way we can represent our nuclei. So nuclei is represented as ZXA. ठीक है, तो सबसे पहली चीज है किसी भी न्यूक्लियाई को कैसे रिप्रेजेंट करते हैं. दिस इज रिप्रेजेंटेड एज ZXA. Many times you will find out that they are writing here number of neutrons. In many books you can also find out this type of a denomination. So here whatever they are writing here, that will be number of neutrons. So here we have number of protons, here we have number of neutrons, and this A is the mass number. This A is the mass. So this is the nuclei about which we are aware. But the first nuclear model, or you can say atom or nuclei, first nuclear model of the atom was presented or suggested by Rutherford in 1910. It was Rutherford who first time suggested the nuclear model of the atom. So what is Rutherford model? So first is Rutherford model. We are going to start with Rutherford model. So in 1910, Rutherford was the person who first time suggested some model for the nuclei of the atom. What he did, he performed an experiment where he took so I am drawing a very simple. So here we have an alpha particle source. So it is emitting alpha particles in all possible directions. It will emit alpha particles. This is a alpha particle source. This is alpha particle source. He placed this source in a box made up of lead. He placed this source in a box that is made up of lead, and there was a small hole. There was a small hole in this lead box. So suppose this is the lead obstacle or box in which a small hole is there. So alpha particles are coming out of this in the form of a fine beam. The thickness of this hole is very small, so these alpha particles, when they are coming out of this, they are very much focused. They are moving as a parallel beam. They are moving as a parallel beam. So from here, this is the, what is this? This is the lead container, a part of the lead container which is surrounding this alpha particle source, and alpha particles are coming from here, and they are striking here, and they are striking here on a gold plate. On a gold plate. This is a gold plate, and this gold plate is surrounded by a fluorescent material film that is of ZNS. ZNS acts as a fluorescent material, and this AU plate, this gold plate, is placed at the center. This is ZNS, zinc sulfide plate. This is zinc sulfide, you can say, plate, and whenever alpha particle will strike on this, there will be a scintillation, and you can find out, okay, alpha particle is striking here. When these alpha particles are striking, they are striking here on this gold plate. Then Rutherford observed few very interesting results. He observed very interesting results, and this type of scattering he has observed. So what he has observed basically, he find out that most of the alpha particles, they are propagating in the forward direction. You can say even 97, 98% or even greater than this number of alpha particles are moving nearly undeviated. There was no scattering, there was roughly no deviation, or if there was some deviation, it was roughly 1 degree or 2 degree or 3 degree. Apart from this, a smaller fraction of the alpha particles, they are scattered by larger angles. And a very, very small fraction, roughly 1 in 1 lakh particles, that is reflected back, means for this scattering angle will be 180 degree. If this is the original direction, so one of two particles, they are reflected in the back direction, so this scattering angle will be 180 degree. So this was a very interesting result. To explain the result of this experiment, first time Rutherford gives some nuclear model. He wanted to explain these results. For this, he made few hypotheses or few assumptions. Basically, he assumed something, and on the basis of that assumed thing, he explained result. What he was saying, first time he was saying that most of the positive charge, or you can say all of the positive charge, and most of the mass. So he gave the first assumption that all the positive charge and most of the mass of the atom is concentrated in a very small volume at the center of the atom, and this is this central place where all the positive charge and most of the mass is present. That is known as nuclei. Number two, this was his first thing. Second, he was saying that this nuclei is surrounded by the cloud of the electrons. Number two, nuclei is surrounded by cloud of electrons. And because these electrons are carrying negative charge, they are compensating the positive charge of the nuclei, and as a result, this atom is electrically neutral. His third assumption was that these electrons and nuclei, they are held together by electrostatic attraction. So he made these three conclusions here. It's not conclusion, basic. He made these three assumptions. And on the basis of these three assumptions, what he was saying? He was saying when an alpha particle is moving towards the nuclei. So what he was saying, okay, here we are bombarding this aluminum, this is gold foil. This is gold foil. So when we are bombarding this gold foil with the help of alpha particles, then alpha particles are interacting with the atoms of this gold foil. And because most of the atomic volume is nearly empty, in the outer region we have only electrons whose mass is negligible. So automatically outside the nuclei, most of the space is empty. And when alpha particle is moving, suppose this is nuclei, this alpha particle is coming here, it will experience some type of electrostatic repulsion, because this alpha particle is carrying positive charge, this nuclei is also carrying positive charge, both are carrying positive charge. So automatically when they will interact, they will exert repulsive force on each other. So what he was saying, because most of the atom is empty except the nuclei, so you can consider in this way, if this is the atom, suppose, and this is the nuclei here. So when alpha particle is passing through this region, then the interaction between this nuclei and this alpha particle is negligible, because this region is nearly empty, and interaction between this alpha particle and this nuclei is negligible. So due to this reason, this alpha particle will move nearly undeviated. Second case, most of the particle will pass through this empty space, because if you calculate its volume of this empty place, this is very, very large as compared to the volume of this nuclei. But still, few of the alpha particle, they will pass close by to this nuclei, and due to this reason, they will experience a significant Coulombian repulsion. So as a result, they will deviate from this path by larger angle. Third was, if an alpha particle is coming into the line of this nuclei itself, if an alpha particle is coming in the line of this nuclei itself, so automatically there will be a very large repulsive force. It cannot enter into the nuclei, rather this nuclei will repel this alpha particle, and it will go back, it will scatter back, or it will backtrace its path. So all these three results are explained in this way. all results were explained by the Rutherford in this way, and with the help of this type of hypothesis, he was able to find out the order of the size of the order of nuclei. So with the help of this experiment, he was able to find out that the radius of the nuclei is 10 to minus 14 to 10 to minus 15 meter. He was able to find out, first time someone was able to find out that the radius of nuclei is of the order of 10 to minus 14 to 10 to minus 15. This was an important result from this experiment. Later on, he developed a mathematical model for this. But for this model, he considered two very important things. He made two very good assumptions, and assumption was that this alpha, first assumption was that this alpha particle as well as this nuclei, they are acting as point charges. So during his mathematical calculation throughout, he was assuming that this alpha particle as well as this nuclei, they are acting as point charges. This was his first assumption. Second assumption was that this nuclei is so massive, or this nuclei is sufficiently massive that it will not be displaced in this encounter. So first was that this alpha particle as well as this nuclei, they are point charges, and second, this is significantly massive. This nuclei is significantly massive, and it is too massive with respect to this alpha particle that it is not going to be displaced. It is not going to be displaced in this encounter or in this scattering. These two assumptions he made, and on the basis of this, he find out some good relations. I'm not going to drive those relations here. They are not required from exam point of view, but I will give you the relation. What type of relation he find out? He find out two very good or important relations.
Sir, is there a method to calculate the electrons?
Pardon?
Is there a method to calculate the electrons for any nuclei?
Electrons for any nuclei? Electrons inside the nuclei?
Yes, sir. Like in different shells, KL, MMC.
Pardon, बेटा मैं आपको क्वेश्चन नहीं समझा, क्या कह रहे हो आप?
Sir, I am asking that is there any method to calculate number of electrons
Inside the nuclei?
Yes, sir.
Actually, electrons doesn't exist inside the nuclei. Inside the nuclei, electrons doesn't exist, and we will prove, and we will show you by various methods that electrons cannot exist inside the nuclei. तो मैं बेटा क्योंकि इलेक्ट्रॉन एग्जिस्ट ही नहीं कर सकते तो हम उसे फाइंड आउट कैसे करेंगे, लेकिन आई विल प्रूव हियर इन दिस क्लास that electrons cannot exist inside the nuclei. There are 3-4 methods with the help of which we can prove that electrons cannot exist here. Even if you are talking about beta particle emission, then in beta particle emission, nuclei is emitting electrons as well as positrons. But these electrons and positrons, they are created only at the time of emission. They do not exist inside the nuclei, rather they are created at the time of emission itself. So we can easily prove in this class that electrons do not exist inside the nuclei. I will prove this. Basically, there are two models for the nuclei. I will discuss both. One is electron-proton model. First model that was given for the nuclei, they were suggested that both electrons and protons exist inside the nuclei. This was the first model. Later on, they find out some contradictions, so they move on, and later on, they developed the neutron plus proton model. Neutron plus proton model of the nuclei. So I will discuss both. So here you will find out that electrons cannot exist inside the nuclei. Okay. So first relation they find out, or Rutherford find out, that was the relation between the scattering angle theta and impact parameter rather. B, this is denoted by B. But first question arises, what is the meaning of scattering angle and what is the meaning of impact parameter? You can consider this with the help of this diagram. Suppose this is the nuclei and this is the line of action of this nuclei. This is any line of action. Suppose I'm drawing another line here, line parallel to this. Suppose a particle or this is alpha particle, it is coming towards the nuclei. So this is alpha particle which is coming towards the nuclei. Then minimum distance between the nuclei and this alpha particle, when there was no force acting in between alpha particle and this nuclei, when there was no force or repulsion was taking place in between this alpha particle and this nuclei, at that time this minimum distance, this is known as impact parameter. And what will happen? It will move like this, and after this it will scatter in this direction. This is alpha particle. So this is interacting with this nuclei and this is, but when there was no interaction, then the minimum separation between the nuclei and this alpha particle, this is known as B, impact factor. So this is B. This impact factor is very important for scattering. Another is the scattering angle. So here this is moving like this. This line is representing the asymptotic line for this alpha particle movement. And after the scattering, again it is moving in a straight line. So if I consider this asymptotic line and here I backtrace this, then this angle between the asymptotic direction of the incident alpha particle, asymptotic direction of the incident alpha particle, and the asymptotic direction of the scattered alpha particle, the angle between these two asymptotic directions is known as theta, the scattering angle. This is known as the
So could you please repeat, theta?
I will repeat. So basically alpha particle is coming from this side. As it is moving in the forward direction, then interaction, this is positively charged, So as it will move here in this direction towards the nuclei. In between them, repulsive force will increase. And due to this repulsive force, it will follow this direction. Now I have to find out the scattering direction. What will be the scattering direction? So initially it is moving in a straight line, and after scattering after sufficient distance, it will again move in a straight line direction. So what will be the scattering direction? अगर मैं बेटा ये जो प्लेन पार्ट था, लीनियर पार्ट था, अगर मैं इसका एसिम्प्टोटिक डायरेक्शन कंसीडर करूं, इसके पैरेलल लाइन बना लूं, तो दिस विल बी द पैरेलल लाइन हियर, दिस विल बी द एसिम्प्टोटिक लाइन, जितना क्लोज बना सकते हो उतना बेटर है. So this is the asymptotic direction of incident alpha particle. And अगर मैं इस लाइन का बेटा asymptotic behavior, asymptotic direction लूं, then this is the asymptotic direction of the scattered alpha particle. अब इन दोनों को बेटा जहां मिलाओगे इनके बीच में एक एंगल बनेगा. This angle is known as scattering angle. So scattering angle is the angle between the asymptotic directions, of incident alpha particle and scattered alpha particle. This is known as, ठीक है?
जी सर, thank you.
Now he gave a relationship between them, and what was the relationship? This was B equal to Z E square upon 4 pi epsilon naught K cot theta by 2. This is the relation. This is the relation between the impact parameter and this cot theta. This is the scattering angle. This is the relation. There can be numerical on the basis of this, and this K. You are aware what is Z? Z is the charge number of this nuclei. E or 4 pi epsilon naught आपको पता है. K is the kinetic energy of the alpha particle. Here you can write this K is the kinetic energy of the alpha particle. K is the kinetic energy of the alpha particle. This theta is the scattering angle. From this result as well as from this experiment, one can observe that when B is greater than R, R is the nuclear radius. When B is greater than R, then this theta scattering angle is nearly equal to 0. This is nearly equal to 0. When B is greater than R, then theta is nearly equal to 0. Second point is when B is of the order of R. When B is of the order of R, ये होता है बेटा 10 to the minus 15 मीटर के आसपास. R is of the order of 10 to the minus 15 meter. When B is of the order of R, then it will be responsible for larger scattering angle, larger theta angles. This will be the condition for larger theta angles. And when B is less than R, then theta will be nearly 180 degree. It will be backscatter.
Sir, could you please explain again what is the definition of B? How we have defined the distance?
हाँ बेटा, अब मैं बताता हूँ. ये तो ठीक है, ये हमने कुछ जो उन्होंने रिजल्ट और जो कंक्लूजन लिखे, अब मैं इसे फिजिकली बता देता हूँ बेटा आपको. सपोज ये मेरा न्यूक्लियाई है बेटा. दिस इज न्यूक्लियाई. और बेटा ये मेरा एटम हो गया. इस सर्कल बना लेना बेटा ठीक से, मैं इसे ठीक से बना नहीं. दिस विल बी अ सर्कल. And suppose this is line of action. अगर बेटा अगर सपोज मेरा अल्फा पार्टिकल बेटा इससे यहाँ इंसिडेंट हुआ. सपोज अल्फा पार्टिकल इज इंसिडेंट हियर, and this is B, and this is R. So when this B is greater than R, automatically there will be there will be negligible interaction between alpha particle and nuclei, and this theta will be nearly 0. Second case can be, this is the first case, when alpha particle is nearly passing close to the nuclei. So here this is alpha 2, and here this B is greater than R. B is greater than R or roughly of the order, दोनों का order 10 power minus 15 के order का है, then what will happen? It will be scattered at larger angle. This is the second case. This is B. Minimum separation between the line of action of this alpha particle and this nuclei. Perpendicular distance between them. When interaction between this alpha particle and this positively charged nuclei is nearly zero, when it is at large distance. So this is known as B. But when alpha particle is passing, yeah, I say beta और कम कर दो. Here, so when alpha particle is very close to line of action, then this separation is B, but this is B. And when this B is less than R, this B is less than R, what will happen? This will move. Here this alpha particle, this alpha 3, this will have some kinetic energy, but when it is moving in the forward direction, it is interacting electrostatically with this nuclei, and its kinetic energy is converting into the potential energy. It is working. It is losing its kinetic energy as a opposition to this repulsion. It is moving forward as it will move ahead, its velocity will decrease, and there will be a time when its velocity will become nearly zero. It will become zero when all of the kinetic energy will become equal to the electrostatic repulsive energy. Then what will happen? It will move in the backward direction. It will move in the backward direction because this alpha particle as well as this nuclei both have positive charge. So there is a repulsion. Due to this repulsion, it will be scattered back. So this is the third case when B is less than R. Well, B is less than R, and we can use this. B less than R to calculate. We can use this third condition, B less than R, to calculate the distance of minimum. The distance of, क्या कर सकते हो बेटा? The distance of closest approach. You can calculate distance of closest approach. So with the help of this, I can calculate the distance of closest approach. How we can calculate this? Suppose at this point, kinetic energy of this alpha particle is K. This is equal to kinetic energy. This is K. This is equal to half mv square. And when it is moving in the forward direction, its velocity is decreasing, but repulsive potential energy is increasing. And at a particular distance, this distance is known as distance of closest approach. This distance is known as distance of closest approach, and at this distance x, velocity becomes zero, and all of the kinetic energy is converted into the potential energy. What will be the potential energy? This will be 1/4 pi epsilon naught. अल्फा पार्टिकल पर बेटा कितना चार्ज होता है? +2e. अगर Z नंबर है न्यूक्लियाई का, then it will have Ze upon x. And kinetic energy will be how much? This will be, suppose, half of mv square. Now you can choose any value of Z. Suppose I am taking this m is alpha particle. This is m alpha. Suppose Z is equal to 20, I think. This m alpha, kitna hoga beta? This will be 4 times, nearly 1.66 into 10 power minus 27 kg. ठीक है, ये हो गया. V को मान लेता हूं मैं नॉन रिलेटिविस्टिक रिजीम में 10 पावर 7 मीटर पर सेकेंड. अगर आप ये बेटा सारी चीजें अज्यूम कर लो, then you will find out that this r, this distance x, it comes out nearly of the order of 10 to the power 14 meter, minus 14 meter. This is equal to x equal to 10 to the power minus 40. So this is the distance of closest approach. इस काइनेटिक एनर्जी के साथ इससे आगे नहीं जा सकते, बट स्टिल आप जिस डिस्टेंस तक भी ये अल्फा पार्टिकल पहुंचा, दैट इज वेरी क्लोज टू द न्यूक्लियाई. So automatically radius of the nuclei will be lesser than this. Radius of the nuclei will be lesser than this. So on the basis of this simple experiment, by finding distance of closest approach, he was able to prove that the radius is less than 10 to the minus, radius of the nuclei is less than 10 to the minus 14 meter. So on the basis of this, he proved that. Later on there were different methods developed, and they find out later on different methods developed, and even before various scattering experiment, what they find out that this radius is, in general, radius is given by r equal to r naught a to the power 1 by 3, where this r naught is a constant, its value is 1.1 to 1.5, कहीं भी हो सकती है इनके बीच में, इतने फॉर्म में, into 10 to the minus 15. So later on, with the help of various scattering experiment with different type of nuclei, they find out, or they establish a relation between the radius of the nuclei and this mass number. And this mass number. हाँ जी.
Excuse me, sir. सर ये जो आपने वेलोसिटी कंसीडर करी है, दिस वेलोसिटी आपने रैंडमली कुछ भी कंसीडर कर लिया ना 10 की पावर 7 मीटर पर सेकंड?
हमने नॉन रिलेटिविस्टिक रिजीम में लिया बेटा ये, तो 10 पावर 7 एक सिग्निफिकेंट वेलोसिटी होती है. अगर आप जिस टाइम की बात कर रहे हो बेटा, उस टाइम अल्फा पार्टिकल को एक्सीलरेट करना भी मुश्किल था, तो उन्होंने वो वैल्यू चूज की जिस वेलोसिटी से वो अल्फा पार्टिकल को एक्सेलरेट कर पाए. आज तो बहुत सारे एक्सेलरेटर्स हैं, इवन वी कैन गो टू द रिलेटिविस्टिक रिजीम आल्सो, बट एट दैट टाइम इन 1910, ठीक है, at that time it was very difficult. There was no such accelerators were not present, but at that time they were able to accelerate these particles by applying a potential difference. They can accelerate up to 10 power 7 meters per second. So they were using this parameter at that time. आप अगर इससे ज्यादा भी वेलोसिटी ले लोगे तो क्या होगा बेटा, और ज्यादा आगे तक पहुंच जाएगा. So we will be more closer to the nuclei. But they were not saying that in this experiment, they were not claiming that they have find out the radius. But what they were claiming, that radius of the nuclei is less than 10 power minus 14 meters. 10 power minus 14 meters. So this was a good approximation. Later on, we find out that the formula for the radius of the nuclei is r equal to r naught a to the power 1 by 3. This is the mass number. ठीक है, इससे आगे बेटा कल डिस्कस करेंगे. ठीक है बेटा
जी. थैंक यू सर.
थैंक यू सर.
वेलकम बेटा.
Thank you,
मोस्ट वेलकम. ओके बेटा, कल मिलते हैं नेक्स्ट क्लास में.